Okay, so we've done two examples thus far, both the same scenario, but just thinking about it differently by defining our system or our scenario slightly differently. We already wrote the equation when we did not account for friction. Then we wrote the equation when we accounted for friction. Now what we're going to do is we're going to write the equation for when we do not account for friction, but we are not accounting for the spring in the system. So it says to only include in this problem the car and the earth in the system. Okay, so that's going to change things a little bit. So now that I've gotten rid of the spring and the track from the system, that means I'm not accounting for friction. So it's going to look more like this equation. In other words, there's not going to be any thermal energy at B. So we know that. So I'll go ahead and move that out of the way. The question is, and this is a really important point, when I say to not include the spring in the system, that does not mean the spring is not doing anything. The reason the car is going up the hill is because the spring is applying energy to it. So now the question is, how do I account for the fact that the spring is still doing something? It's just not in the system. Well, here's how I do that. I like to specify what things are outside the system. So in this case, I'm taking the spring from inside the system and I'm putting it outside. That's why it's out of the circle. So at position A, we know that the energy is in the spring, not in the car and earth. So therefore, these L's show the energy that's in the system, which is a car and earth, not the spring. And E elastic represents energy from the spring. So therefore, because the L's represent the energy that's in the system, these bars of energy cannot be present in this L because they're not in the car earth system. They're at the spring. So I'm dragging them down to be by the spring, like so. Now at position B, remember that spring is not compressed at all, and so therefore it's at the very top of its motion. It's not moving, and there's no thermal energy because there's no friction. So therefore, I've got all gravitational energy. So wait a minute. These 3 bars of energy at position B were just somehow created? No. If you remember from Chemistry 1, and some of you guys, I made videos to explain this in the problems that you came up with. But this energy from this gets donated to the system. And the way that I show that is by putting energy into the system. In other words, I'm showing that 3 bars of energy are being added to the system from the spring, and then that turns into gravitational energy. So now the question becomes, how do I write that equation? Well, the way that I write that equation is the energy at position A. Well, wait a minute. There is no energy at position A. What could I call that? Well, any energy that's entering the system is something that we call work. And the way that we represent that is with a capital W. And so we're going to say work, or the energy entering the system, is equal to the EGB. So in other words, the work entering the system equals the gravitational energy at the top. And so this would be the scenario when no friction, but spring out of system. And that's what that equation would represent, like that. Hopefully that makes sense. The key thing about this is that work is energy entering or leaving the system. That's a key term, work.